Hello everyone. I was originally thinking about just kind of writing down a solution for these problems for you guys to have them, but I figured since I had the opportunity and I'm trying out the YouTube thing here, I thought I would just walk through it in person as well. So this might be a little bit more beneficial than the study session part of this. This is number 14, by the way. We really had to rush through these problems, so I figured I'd take the time to explain it. So, what we have going on here is that we have a lighthouse that from the nearest point on this shoreline, so this area right here is the shoreline of a just some particular shore. The closest point is 4 kilometers away from the lighthouse. And what we see happening is that we have the lighthouse that's spinning at a particular speed. In this case, that speed being 3 revolutions per minute. So that means that each minute that this lighthouse spins around, it will have spun 3 times all the way around. And we're given that we want to know when we are 1 kilometer, when that light, this distance right here is 1 kilometer away, we're wanting to say what is the change in that distance along the shoreline. Okay, so the key thing there is along the shoreline. This is the shoreline right here. We want to make sure that we are going along this way. So dx over dt is the thing that we're looking for in this problem. Okay, so the first step that we would suggest, right, and what I've done here is I've labeled this shoreline distance as x, and I've labeled the kind of hypotenuse of this triangle I have here as y. Okay, we have a right triangle in this situation, so it's handy. This allows us to get a few formulas, which we can kind of work through, talk about each one, and see maybe how some of them can help us, right? So the first, of course, just using this in general, we won't plug in the 1 yet just to see what's happening. It's the Pythagorean theorem. Whenever I have a right triangle, I know that a right triangle, that the sum of each side squared, so in this case I will do 4 squared plus x squared is going to be equivalent to y squared. Okay, so once again, we may not use the derivative of this, or we might, it just depends, but we know we can get at least some numbers from here. I could easily figure out what y is supposed to be in this case, right? Next, we can talk about each of our main 3 trig functions, right? So, if I am thinking about SOH, CAH, TOA, right? We know that sine is the opposite side from our angle over the hypotenuse of the triangle. So sine of theta is equal to the opposite, which is x, over the hypotenuse, which is y. Okay, so there's maybe a useful equation. Cosine is going to be adjacent over hypotenuse, so that is going to be the adjacent side of the triangle, which is 4, over the hypotenuse of the triangle, which is y. So we get this. Okay. Finally, we're going to get that the tangent of theta is equal to the opposite side of the triangle, x, over the adjacent side, which is 4. So this one, might come in handy. It really depends, right? We just have to see. We know right now that we want to solve for dx over dt, right? So what we could do, right, we want to relate dx over dt to kind of the other derivative that I know, which in this case is this d theta over dt, right? So my idea here is maybe we can just take this formula, the tan theta is x over 4, and we can take the derivative of that. Okay, so let's walk through that, right? So tangent theta, so I'll bring that up here. We're going to get that the tangent of theta is equal to x over 4. So with this being the same thing as 1 over 4 times x. And if I take the derivative of both sides, so I'm going to write, take the derivative like this, we see that we get the derivative of tangent theta is secant squared theta. But of course, we're working in terms of our related rates, so I'm going to have d theta over dt involved. And this is going to be the same thing as 1/4 times the derivative of x, which is 1, times the derivative of x with respect to t, right? dx over dt. Once again, we're working with our related rates. And we come out to this. So that's actually pretty handy. We could really get our dx over dt pretty easily. I know this. The only issue, foreseeable issue at this point, is I don't know what exactly secant squared theta is supposed to be, or what theta is. You could go through and take one of these equations down here and solve it exactly for theta based on your one here, maybe the tangent theta equation. But that's going to be really difficult to plug in and try to solve for, because this does actually end up giving us a nice answer. So what we're going to do is I'm going to go ahead and solve this for dx over dt, because that's what we want, dx over dt, and this is going to be equal to 4 secant squared theta times d theta over dt. Great. Now, how do I go about finding secant squared theta? Well, let's think about a useful tip that we have, right? Which is the fact that secant theta is the same thing as 1 over cosine theta, right? And that's something you learn in trig. So instead of writing secant squared theta, I can rewrite this as 4 divided by cosine squared theta d theta over dt. Okay, now we know from our equations, right, that cosine theta is 4 over y. Now I don't know what y is yet, but I could solve for it at this specific point using the Pythagorean theorem. So let's do that. So I know we have 4. That's always going to stay the same. 4 squared plus x, which at this current point, right, the point of having this rate is 1 kilometer. And this is going to be equal to y squared. So whenever you add this side together and take the square root, we're going to be left with that y equals the square root of 17. Which leads us to say that though we don't know the exact value of theta at this point, that cosine of theta at this point is the same thing as 4 over root 17. Great. And that's exactly what we need over here. Now, one last thing that we need in order to solve this problem is I have this d theta over dt that I need to plug in, but I can't really use revolutions because that's not going to give me the answer I want or give me it in the form that I want to. So what we typically do when we have a problem like this where we deal with revolutions is I want to take that revolutions and convert it to radians. So I'm going to do that. So 3 revolutions per minute, and then I want to multiply by every 1 revolution, right, of any circle as we go around. That's the same thing as 360 degrees, or in the case of radians, that's 2 pi. That's 2 pi radians. Okay, so I can rewrite this using the fact that 1 revolution is the same thing as 2 pi radians, which gives us that our d theta over dt is the same thing as 6 pi over radians, and then that's per minute. Okay, so final step, we're going to take that and plug this in and plug the fact that cosine theta is 4 over root 17 into our equation. So I'm going to get 4 over 4 over root 17. I'll rewrite that real quick for us. Root 17 quantity squared times 6 pi radians per minute. And just a reminder that this 4 is in kilometers. And so when we multiply the kilometers by the radians, that will give us kilometers. So I'll work out the math a little bit for us. 4 stays the same on top. We get 16 over 17 when we square that, times 6 pi radians per minute. Okay? And as a final step, you can go through and take things and cancel out. This 4 is going to stay. I can take the 16 over 17 and flip that. So I get times 17 over 16. And then multiply that by 6 pi. And then things are going to cancel pretty nicely here. So 4 and the 16 reduce. I get 1 here and 4 here. And the 6 and 4 can also reduce again. That'll leave me with 3 here and 2 here. So then if I do 17 times 3, and then I divide that by 2, I'm going to be left with, writing a better equal sign here, 51 pi over 2 kilometers per minute. And this is the answer in your key. Alright, hope that helped for problem 14. Thank you guys so much for watching.